Trigonometry, three-dimensional problems. So we're going to have a look at solving problems that require the use of thinking in 3 dimensions and using Pythagoras' theorem and trigonometry. We've already done some work on Pythagoras' theorem in 3 dimensions. We're simply going to extend this to the concept of trigonometry. So have a look at the cuboid in this example. We're going to start off with a simpler example. We're going to calculate angle GBC. So the first crucial thing is to make sure we know which angle this actually is. So if we draw a line from G to B and then back across to C, this is the angle that we need to work out. I'll call it X. I'll join C back up to G, and then we have our right angle triangle on one face of the cuboid with a right angle at C. So let's have a look at this more clearly. So I've sketched out the diagram again, and I've lifted the triangle that we are working with into another diagram over here. We're going to label the sides of our right angle triangle, first the hypotenuse, then the opposite, then the adjacent. Let's highlight the 2 sides that we are interested in, the opposite and the adjacent. And this, of course, tells us that we are looking at using tan. So we might like to draw out a SOHCAHTOA triangle. And then this tells us that tan of x is equal to the opposite divided by the adjacent. So tan of x is equal to 5 divided by 8. And x is then equal to tan to the minus 1 of 5/8, which we can calculate using a calculator. This is equal to 32.005, which rounds to 32.0 degrees to 1 decimal place. Let's look at the second part of this question. We've now got to calculate angle GAC. So this time we're going to join G all the way across to A, back along to C, and then up to G again. There's the right angle at C, and the angle that we're looking for we'll call X over here. Now, before we calculate this, it's worth looking at a little bit of vocabulary. This angle GAC is referred to as the angle between the line AG, which is this line here, and what we call the plane ABCD. So the plane just refers to this face here, the base of the box. And you can think of a plane as a 2-dimensional space. And the angle between the line AG and the plane ABCD is this angle X here. We're going to have to get used to using this terminology. It's going to pop up in some of the later examples. So as you can see, I've drawn out the diagrams hopefully a little bit more clearly. Here's the angle X that we're looking for. I've sketched out the right angle triangle AGC again, but unfortunately we only know GC, the distance 5 centimetres. We don't know either AG or AC, so we'll have to find out one of them if we're going to proceed. I want you to have a look at this triangle, the triangle that joins up A, C and D. It's a right angle triangle, and although it's difficult to see, there's a right angle here at D. If you want, get a shoebox, look at joining up 3 vertices of that shoebox and you will see the right angle triangle form. I've drawn it out again over here so you can see it a little bit more clearly, and we've marked in the distances C to D and A to D. Let's work out this measurement AC, which is the hypotenuse. So I'll call that A, I'll call this B, and of course C is our hypotenuse. So up here we'll do the calculation. Let's write out Pythagoras' theorem. We have 2 sides, no angle, so this is going to involve Pythagoras. A squared plus B squared equals C squared. 8 squared plus 6 squared equals C squared. So C squared works out to be 100, and C equals 10. This is another Pythagorean triple. We've talked about those before. We have what we call a 6, 8, 10 centimetre triangle here. So A to C is 10 centimetres. Look at the main diagram again. AC is this measurement here, 10 centimetres, which means it's this line here, A to C. So again, let's take the right angle triangle separately to have a look at it. AC is this measurement here, and it's 10 centimetres. We can now use a bit of trigonometry to work out the angle GAC, which we've called x. Here's the hypotenuse, here's the opposite, and here's the adjacent. We're interested in O because we know it, and A because we know it, so it's another TOA situation, or we're using tan. So remember, tan of x is equal to the opposite divided by the adjacent. If it helps, let's stripe out the t so you can see O over A. X is then equal to tan to the minus 1 of the opposite over the adjacent. Sorry, should have said that's 5/10 there. So that's tan to the minus 1 of 5/10, which we can input into our calculators. This then equals 26.565, 26.6 degrees to 1 decimal place. Example 2, things are going to become a little bit more complex. Starting simply again to begin with, let's calculate angle BFC using this triangular prism. So let's join these points up. So B to F, that's across here, across to C, and then join B and C. So the angle BFC is this angle here, which we'll call X, and there is a right angle which is over here. Imagine you were facing this prism right in front of you. There's a rectangular face at the front, so BEFC is a rectangle, so this is 90 degrees. Okay, so how are we going to calculate this angle? Let's have a look at the next part of the video. Now, I've sketched out triangle BFC a little bit more clearly. Remember, this is the angle X that we're looking for. Now, the only measurement we know is this one here, C to F, which is equal to 10 centimetres. We don't know either of the other two, but we could find this measurement, B to C, quite easily because we have a right angle triangle ABC. I haven't drawn it out again because it should be quite clear. I'll just shade it in case anybody can't see it. Let's label the sides. There's my hypotenuse, there's A, there's B. So again, using Pythagoras' theorem, A squared plus B squared equals C squared. 6 squared plus 4 squared equals C squared. So C squared is then equal to 52. So C equals the root of 52. And again, we're not going to simplify this third further. We'll leave it as root 52. So BC is root 52, which means that we can now work out angle X. Let's label our right angle triangle BCF, hypotenuse, opposite and adjacent. Identify that we're working with the opposite and the adjacent again. So we are looking at using tan, or the TOA triangle. We know O, we know the value of A, so covering up T, tan of X is equal to the opposite divided by the adjacent. Tan X is equal to root 52 divided by 10. X is tan to the minus 1, the inverse tan of root 52 over 10, and this is equal to 35.795, rounding to 35.8 degrees to 1 decimal place. Now, here's where things become more interesting. Let's read the question really carefully and perhaps highlight some key words. Calculate the angle between the line BF and the plane ACFD. So where's this line BF, first of all? Let's find that line BF. So it's here, joining B to F, like that. Now the plane ACFD is the base of this prism here. Now, how do we know which angle to find? Because there are so many possibilities. Here's the trick. Draw a vertical line down from the highest point, which is B, down to the ground, like that. From there, join the point that you reached back to the point you started from here, which is F. The angle you want is this angle here, because it's the angle between the line BF and this plane which we have shaded in red. Here it is, all a little bit more clearly. Here is our right angle at A, and here's the angle, X, again. Now, I've drawn this particular triangle out again over here. There's angle X. The only measurement we have is AB, which is 6 centimetres. We don't know the other measurements, so we've got to work them out, or work out one of them. So what I'm going to do is work out the distance A to F. Now, to see the right angle triangle, you need to actually look at the base of the cuboid, and hopefully you can see where I've shaded in green, there is a right angled triangle. It joins up point A with point F and point C. And for clarity, I've drawn it out separately over here. So F to C, which is this measurement here, is 10 centimetres. A to C is 4 centimetres. There's a right angle there between AC and CF at C, and the measurement we're looking for is A through to F, which I will call Y. So that's this. So again, using Pythagoras' theorem, we can work this out. This is our A, well, this could be our A, this could be our B. A squared plus B squared equals the hypotenuse squared. So 4 squared plus 10 squared equals Y squared, which gives Y squared equals 116, and Y equals the square root of 116. So this means A to F is the root of 116, here it is, and we're now going to calculate the missing angle that we want, angle X. Hypotenuse, opposite and adjacent. Highlight key information here. So again, it's a TOA triangle because we're interested in O and A. Tan of X is equal to the opposite divided by the adjacent, which is of course equal to 6 divided by the root of 116. So X is equal to tan to the minus 1 of 6 over root 116, which you work out on a calculator. This gives us an answer of 29.121, which rounds to 29.1 degrees to 1 decimal place. So example 3, let's have a look at what we've got to do. Calculate the angle between the line VA and the plane ABCD. So where's this line VA? Let's find that line first of all. We can draw it out, trace over in green, here it is. There's the line VA. Now the plane ABCD, that is the base of this square-based pyramid. It's here. So remember what I said last time? You want to find the angle between a line and a plane. Start at the highest point you've got, which is V. Drop down perfectly vertically till you get to the ground. And this point here will be in the centre of the base, because V is directly vertically above that. And then simply join back to the starting point at A, like that. And there is your right angle triangle. You'll always have a right angle there, and the angle that you want is here. Call it X. And here is everything we need. So the right angle we sketched a second ago was over here. Here's the angle that we are looking for. And as before, I've sketched this out separately over here. You can see it in this right angle triangle. There's VO, like that. There's VA, like that. And here is AO, like so. And there's the angle X that we want to find out. Unfortunately, we do not as yet know the value of AO, and we do not know the value of VO either. There are now several different ways in which we can calculate the measurement AO. This is how I'm going to do it. It's not the only way to do it. You can do this in different ways. Feel free to experiment, but you should get to the same correct answer if you've done it correctly. So I want you to imagine we actually join up A to C like that. This is a square-based pyramid, so there's a right angle over here. And let's shade in that triangle there. It's the same as this triangle over here. Now, what I'm going to do is I'm going to work out the measurement A to C. So using Pythagoras' theorem, I could say that 8 squared plus 8 squared is equal to AC squared. So AC squared is equal to 128. AC equals the root of 128. Now, if you simplify that, you will find that comes to a value of 8 root 2. If you want to do that in full surd form, let's have a look. The root of 128 is the root of 64 multiplied by the root of 2, which is 8 root 2. Now, how do we find AO? Well, O is in the centre of the base of the pyramid, so O is here. So that means that AO is simply a half of AC, which is a half of 8 root 2, which is 4 root 2. So A to O, which we can mark on our separate triangle over here, is 4 root 2. And remember, we're trying to find angle X. Hypotenuse, opposite, adjacent. Let's highlight what we're interested in. We know the adjacent, we know the hypotenuse. This time, we need to use cosine. I'm going to draw out the K triangle. We know what H is, it's 10. We know what A is, it's 4 root 2. So we're looking for C. So cos of X is equal to the adjacent divided by the hypotenuse, which is equal to 4 root 2 over 10. X is then equal to cos to the minus 1 of 4 root 2 over 10. Input that into your calculators. This works out to be 55.55, etc., 55.6 degrees to 1 decimal place. Now for part 2 of this question. Calculate the angle between the plane VBC and the plane ABCD, so the angle between two planes. Let's shade in these planes. So VBC is this triangular face here. ABCD is the base of the square base pyramid. The angle between them, remember what I keep saying, start at the highest point, like so, drop right the way down, and then let's go across like that. There's the right angle triangle. There's the right angle that we want. The angle between the two planes is the angle between the green and the yellow shading, which is this angle over here. This point here is the centre point of the base, so it's in the middle of this square, and this point here, M, is the middle or the midpoint of the side BC. And here we have all of our sketches laid out neatly to have a look at. The angle we're looking for, remember, is this angle here. So it's angle VMO, O being the centre of the base, M being the midpoint of BC. And I've sketched it out again over here. So this distance from there to there, O to M, is halfway across the square. It's parallel to that measurement here. It's 4 centimetres. Here's angle X, and we need to find either VM or VO in order to be able to proceed. You can actually calculate either VM or VO. It doesn't matter which. At the very end of the question, you should still get the same answer for X if you've done it correctly. I have chosen to work out the distance V to M, and there's a right angle triangle here, VMC, with a right angle at M. I'm going to shade this triangle in so you can see it. Here it is. And I've recreated it over here. Look at the letters to help you work it out. VMC. Now, again, we know that M to C is 4 centimetres. We know that V to C is 10 centimetres. We want to work out what VM is, the side that's highlighted in blue in both diagrams. So, Pythagoras theorem again, A, B and C. A squared plus 4 squared equals 10 squared. A squared then equals 10 squared, subtract 4 squared. So A squared equals 84. So A equals root 84. Let's leave it like that. I'm not going to simplify the third. This measurement is root 84. So here we have root 84, and here again V to M is root 84. So now we have enough information to find angle X. The hypotenuse is here. The opposite is here. The adjacent is here. Highlight the key information. There we have it. We have A and H, so we're using K again, or cos. We know A, we know H. Cos of X has got to equal the adjacent divided by the hypotenuse, which is 4 divided by root 84. X is then cos to the minus 1, 4 over root 84. Input that into a calculator. This is then 64.123, etc., 64.1 degrees to 1 decimal place. So now, to review, you should hopefully be able to calculate the angle between a line and a plane, and the angle between two planes. Remember that trick of dropping down from the highest point back to the ground, and then joining up back to the beginning again to create your right-angled triangle.